Hello, physics students. This is the next slide set on accuracy, precision, and significant figures. We will have already seen some of these notes covered in class. This is being posted so you can review and replay as many times as you find necessary. So if you will recall from our discussion in class, accuracy and precision, as demonstrated in this grid coordinate of accuracy on the x-axis and precision on the y-axis, can fall into several different types of scenarios. In the upper right quadrant, you can see when precision and accuracy are high, the analogy would be to a target that the, say, arrows are all close together and in the middle of the target. They are both repeating, they're always giving the same value, and the value is true. It's on the mark. It represents hitting the target. You're getting right what you want, a bullseye. The other alternative is the lower left quadrant, where they're both low accuracy and low precision. Here we see the red dots spread wide apart around the target, and they neither agree with each other nor are they close to the true value, the center of the target. When we stop and look at high precision with low accuracy in the upper left quadrant here, we see that the values are all together, that they're giving the same number, but they are not near the bullseye. They are not right. They are consistently wrong, which is reassuring in some cases because we're obviously making an error, but it's always the same error. And finally, in the bottom right quadrant, we see here that we have high accuracy with low precision. Our numbers are scattered, but they are all relatively close to the center, to the true value. These represent what happens when we actually measure. You may recall from class that we attempted to measure the length of the desk in the lecture hall. We tried to find out exactly how wide the desk was. And when we did so, we came up with many different values, each for a different person. Ideally, we would always come up with the same value, the exactly right answer, but this just does not happen when we're actually measuring things. Frequently, the values are spread out. And this is how we describe them. We say if they are showing the same numbers, close grouping of numbers, they are precise. And if they are in fact on target for what we know to be the true value, something that you might look up, then they are accurate. We are searching for something that is both accurate and precise, as we see in this grouping here. Accuracy refers to how close a measured value is to an accepted value. To evaluate the accuracy of a measurement, it must be compared to the accepted value. You must know the true, tested, and established value. Think, for instance, the density of lead. You know exactly what volume of lead you have, and you're trying to establish how much that should weigh. If it is pure lead, or gold for another example, it would have an exact weight due to its volume or mass per unit volume. Precision, on the other hand, refers to how close a series of measurements are to one another. It's a very common statistical test to see how close the grouping of the numbers are to each other. We begin to see a distribution, often called or seen in a normal distribution, a normal curve, that shows that values are grouped into standard deviations. It's a little bit beyond our course, but precision is how close a series of measurements are to each other. Accepted value is determined by scientists, and it's usually found in a reference book. Your textbook has reference values in the very back jacket, in the back of the book on the outside. You can find several values that you will need through the course, and you will need to reference those at specific times to understand what value you should have gotten in your study. An experimental value is what you find during an experiment. Oftentimes you will be comparing your value with that from the reference, from the text. You will then say how much difference there are between the two and express that as percent error. On another topic, significant figures. When we refer to significant figures, we are inferring that there has been a measurement conducted. And whatever tool was used to make that measure is only able to give you so many numbers that are real. Think of the meter stick that we showed in class. And when we attempted to find a number such as 0.8523, the meter stick did not actually offer that last digit, the 3. We had to infer that value when we took our measurement. As such, we would not necessarily consider that significant. When you use a tool, it only gives you a certain number of significant figures. That is the reason behind significant figures. In this slide, we see the rules that we will go by when we interpret whether or not we have significant figures in a final answer, for instance. We will, in manipulating values, we will come up with a long series of numbers. If it were a multiplication, you might have on your calculator, you might have 7.23561. Are all those real numbers? No, they are not. At the end, when you offer your final answer, you will remove some, you will truncate your answer, and you will only give as many as you know to be significant from the data that you started with. It will always be indicated in the numbers that you start with in your problem. So let's take a look at a couple of these rules. Non-zero digits are always significant. These are non-zero digits, obviously, and here we have 3 significant digits. Final zeros only after a decimal are significant. These 2 zeros seem like they could be thought of as placeholders, but they are not. This has been measured and has been found to be exactly 0.006848. 0.00. They are after the decimal and they are final, therefore they are significant. Zeros between non-zero digits are significant. So as soon as you see a non-zero digit and another one here, whatever's in between it, if you see zeros, they are significant. Even if there's a decimal, you're going to count that as a significant digit. And finally, zeros used as placeholders are not significant. Zeros that start a number and final zeros without a decimal. Notice there is no decimal involved here. When you put that decimal in, these numbers become significant. All right, so this one only has 2, and this one also only has 2. Those are your examples of significant figures. These rules can be found in your textbook and should be memorized. There is simply no other way to keep them for ready use other than to memorize them. Unfortunately, I regret to say that that is the only way to do it. And I believe that that concludes our information on significant figures. Thank you.